the activation barrier that you guys will see in this section is actually the one concept that determines the speed of the reaction, the rate of the reaction. It's kind of like a barrier for preventing the reactant to go into products. If there was no barrier there, then instantly the reactant will convert to products. There has to be some sort of barrier so that it doesn't happen instantly. Of course, if that barrier is lower, then it converts to products faster. If the barrier is higher, then it converts to product slower. And in fact, you need a certain amount of energy to get those chemicals above that barrier. So that's what we're going to see. And this cartoon sort of illustrate that nicely, okay? This person rolling up a bunch of coal over that hill, the higher that barrier, it's going to take longer. The lower that barrier, it's going to be faster and less energy is required. Okay, so that cartoon's pretty good in terms of explaining the speed of the reaction. So the other thing that you should remember is that temperature increases the speed of the reaction. Why is that the case? Because temperature gives the chemical more energy, and in order for the reaction to occur, what needs to happen is that these guys need to collide and break bonds and form new ones. The harder they are in terms of colliding, the more likely those bonds are going to break, okay? Also, the faster they move, they also have more frequent collisions. So these are the factors that we will talk about shortly that increases reaction speed. In fact, if we take this reaction right here, this is the oxidation of iron, and we'll talk about this as well in electrochemistry. And this right here is rust, okay? And what we want to do generally is we want to slow down this reaction. So seeing kinetics, we have, we either want to speed up a reaction or slow down the reaction. This is a case where we don't want that reaction to occur at all, because when iron starts rusting, then the integrity of the metal starts being compromised and it starts to become brittle, and then it'll break down. So we want this reaction to be prevented. We want it to be very slow. And what are the ways to slow down this reaction? Well, we make sure that the iron isn't exposed to oxygen, or there's no moisture, so that the electron transfer will be facilitated. Anyway, that'll be covered in electrochemistry. But if we raise the temperature, we can actually accelerate this reaction. In fact, for every 10 degrees increase, we double the rate of the reaction. So if the reaction is consuming, say, 1 molar per minute, if at 25 degrees, at 35 degrees, it'll be consuming 2 molars per minute, okay? The rate has doubled. So keep that in mind. This is a rule of thumb. For every 10-degree increase, whether it be Celsius or Kelvin, because the delta in Celsius and Kelvin are the same. A 10-degree increase in Celsius is a 10-degree increase in Kelvin. Okay, but it's not a 10-degree increase in Fahrenheit. Remember that from your fundamentals. But every 10-degree increase doubles the rate. Okay, so let's take a look at the kinetic molecular model. Kinetic molecular model is the theory that's presented to explain how reaction occurs. Okay, it comes from the gas laws. And we use gas laws because in gas law, the chemicals are going to not be bound by intermolecular forces. That is, they don't stick together. They collide perfectly. And certain collisions will lead to product formation. So in the kinetic molecular theory, we look at collision theory, which explains factors which again, is based on the speed of the reaction. In a reaction, there must be, in order for a reaction to occur, in order for a chemical change to occur, you got to break bonds and you got to form new ones. Okay, remember the difference between a chemical change and a physical change. A physical change, you don't change the identity. In a chemical change, you change the identity of the starting material. Okay, so In order for a reaction to occur, a chemical change needs to occur, bonds need to break, new ones need to form. Okay, so what exactly will influence that process? What exactly will accelerate or decelerate that process? What will change the rate of that process? There are a number of items that we will look at. One is collision frequency. In order for bonds to break, these things need to collide so that the either the covalent bonds or the ionic bonds that forms them are going to be severed, and then it has the capacity to form new ones. The orientation of the chemical has to be just right because the correct bonds need to break. So you got to get the correct orientation. They got to have enough energy so that when they do collide, they actually do damage. Okay, the bonds actually break. And then the catalyst is an external factor that we'll take a look at towards the end of this discussion. And it's what a catalyst does is it's a chemical or a condition by which it accelerates the reaction rate by taking the path, the mechanism by which these reaction occurs through a different pathway. And by taking it through a different pathway, say a shortcut, then you reach the end product faster. Okay. In the end, the catalyst is going to be regenerated. So it looks like it hasn't even been used up. But what a catalyst does is it accelerates the speed of the reaction by taking it through a different pathway. Okay. So let's take a look at collision frequency. Collision frequency just has to do with how often these things collide. If you take a look at a reaction, say you're in a lab and you put more chemicals in, basically you're raising the population so that there are more encounters. And so what happens is that the higher the concentration, the greater the collision frequency, which generally translates to faster rates. So let's take a look at this right here. We have a four particle system, 2 reds and 2 greens. And the number of collisions are 4. One of the red can collide with 2 of the green, and the other red can collide with 2 of the green. There's a total of 4 collisions. But let's say we increase the population. Let's say we have a 6 particle system. Well, for a 6 particle system, what we have is 8 different types of collisions. Okay. And so what you can see is that by increasing the population based on this model, we increase the number of collisions, which means that we can use this formula. N times N equals the number of collisions. Okay. N particles colliding with N different particles will increase the number of collisions. And we denote that in kinetics by Z, the collision frequency. We denote it by this right here, which depending on the concentrations of A and B is equal to Z. Don't worry about trying to calculate the value of Z, only know that it's a function of the collision frequency, which at this level, you guys don't have to worry about calculating. Just know that that's what that concept means. Okay. If you take PChem, if you're a chem major, then you will calculate this through statistics, but don't worry about it because it's really difficult to monitor all the chemicals in a chemical reaction. There's billions, moles and moles of them. What we need to do is we need to figure out a statistical average in order to model that. Okay. We're not ready for that, at least in this course. The other thing that we need to worry about is the steric factor. Steric factor is just the orientation of the chemical. They have to have the correct orientation so that the right bonds are broken. Here's a reaction between nitrous oxide, NO, and nitrogen trioxide, NO3. And if that reaction occurs, then one of the oxygen in NO3 is transferred to NO. Okay, but it has to have the correct orientation. And again, there is no way for us to follow a chemical in space to make sure that it has correct orientation, but we can do a statistical average, okay? We can figure out some sort of statistic by which these things will have some sort of average by which they do have the correct orientation. But let's go down to the molecular level and see that, okay, these things right here, these are all ineffective collisions. Why? Because they don't have the correct orientation. But one that might have the correct orientation would be something like this, where now the NO has the correct orientation as well as the NO3, so that it breaks one of the oxygen off and then binds it, holds on to that oxygen. So product is formed. Okay, so again, collision frequency and steric factors are two of the topics that we've talked about so far. And then, of course, there's the energy by which they collide. That's the activation energy. That is, when you think of activation, it means that it's going to be key in making that process start. Okay, so this is the energy that makes that process move on to products. And it has to do with the energy the chemical has when they collide. And that's why it's called kinetic molecular theory. And you guys know that kinetic energy is equal to 1/2 mv squared. So it's a function of the mass of the chemical as well as the speed. In fact, it's the velocity squared. So that's the more important factor in terms of this threshold being overcome. But they got to have enough collision so that damage is done. It's kind of like a fender bender, okay? If you're in a parking lot and you just sort of like touch another car, good. There's no damage done. But if you hit it with more speed and velocity, then you can cause a lot of damage. And in chemistry, damage means bond cleavage, bond being broken. And so that's the analogy that I want to show you here, is that if there is enough energy upon impact, then bonds can be broken. Okay, you got to have a minimum threshold. And that we can calculate, that we can figure out in terms of the energetics. The other factors, the collision frequency and the orientation, that's done through statistic. This we can do through statistics as well, but we can also calculate the minimum energy by which these reaction occurs. Okay, so a guy by the name of Savant Arrhenius, that's this guy right here, actually came up with this concept, and he proposed an equation, a mathematical equation called the Arrhenius equation. And it shows nicely how the activation energy, we're talking about the activation energy now. We're not talking about steric factors. We're not talking about collision frequency. We're just looking at the energy required to get this energy past the threshold. Okay. He calculated the energy, the minimum energy for this reaction to progress in the forward direction. Okay. And that's Arrhenius. And so again, it's this concept that the chemicals have to overcome that barrier that separates reactant from product in order for the reaction to progress. Okay, so that's the equation that he proposed. And we use that equation today in terms of understanding how to calculate activation barriers. So before we move on to this topic, I want to introduce you to certain information, okay? Certain types of information that you will need to know in order to work on the assignment that we have for today, okay? Information that you need to know as we discuss the progression of a reaction. The other thing that you should do is, let me go over here, okay, is, let's see, go to the very back of the very end of our slide, this right here. because as we start talking about the concept, you guys can refer to this particular slide and make notes of what each of this definition that I'm going to be talking about mean in the context of this progression diagram. This is a progression diagram. We start with a reactant here. Okay, we start with a reactant here. And we end with a product here. And this is an indication of how the reactant converts to product. That's why it's called a reaction coordinate. Coordinate just tells you the information as it progresses along. Okay, so it's called a reaction coordinate diagram because it tells you the change of the reactant as it converts over to product in the course of the reaction. So take a look at this as I start talking about these concepts that I will be speaking of right here. Okay. So you guys should be able to, after our discussion today, figure out from that diagram, what is the energy of the reactant? It's a point in that graph where you can say, oh yeah, the energy is 25 kilojoules. The energy is 10 kilojoules. The energy is 0 kilojoules, but that's just based on a relative term, okay? At least based on that diagram. Chemicals never really have absolute zero energy. But if we're comparing it to something, if we have some sort of a reference, then we can give it 0, and then we can size everything up based on that. But in general, chemicals do not have 0 energy because it's going to be above 0 Kelvin. The only time it has 0 energy is if it was at 0 Kelvin, and that's theoretically impossible at this point. So energy of the reactant, energy of the product, energy of the intermediate. What exactly is an intermediate in these things? And what is the transition state? Okay, an intermediate and a transition state are not the same. They are completely different species. But all of these are species that exist in time. Some very, it lingers very long. Some is just an instant. Okay, so these are chemical species. If it's chemical species, they have energies associated with it. Let's take a look at chemical process. Chemical process is the process of converting, say, a reactant to a product. How much energy is involved with that? And you guys know that we describe the energy of a reaction as either exothermic or endothermic. So that's a process. Is it an exothermic reaction? Is it an endothermic reaction? Okay, it's not a species, it's a process. We calculate the energy based on final minus the initial. The energy of the product minus the energy of the reactant. Okay, that's a process. It's a calculated value. So the energy of the reaction, that's a process. The activation energy of the reaction, that's a process. The activation energy in the forward direction and the reverse direction, that's a process. Because those are not species, those are energy changes that occurs during a reaction coordinate diagram. Okay, and then there's other terminologies right here. Reaction progression diagram, I sort of explained that. Endothermic reaction, you guys know endothermic reactions are reaction in which energy is required. Energy is a reactant for that process to occur. Exothermic energy is release. Okay, Maxwell-Boltzmann distribution plot. You guys saw that in gas laws. You'll see it here again. And I think I introduced it back when we had Chem 200 review. Okay, it basically shows you the population of chemicals at some temperature. So we pick some temperature and we look at all the chemicals that are exposed to that temperature and calculate their energy, or at least put in some sort of distribution plot the energies of all the chemicals that exist at that temperature. That's a Maxwell-Boltzmann distribution. The transition state is, again, related to the transition state energy. Okay, transition state is where the reactant morphs to products, or maybe the reactant morphs to an intermediate. It's a transition process. And then the intermediate is a chemical that is produced in between reaction steps. So we will take a look at all these terminology and make sure that you understand all these terminologies, because if you don't, then you will have a very difficult time working the group work activity that I gave you. Okay, so let's take a look at a simple reaction coordinate diagram. This is a progression diagram in which NaCl, nitrous chloride, is converted. It basically breaks down to NO and Cl2. And there's going to be two NOCl that combines and collide, and the correct bonds are broken. So the chlorides that collide with each other breaks off and form chlorine, diatomic molecule chlorine, and what you got left over is NO. So right here, this is an energy. And let's say that that energy has numbers. It could be like 25 kilojoules. Okay, we're going to be using kilojoules in this discussion rather than calories. And let's say that this activation energy is, say, 105 kilojoules. So the energy is going to be on this axis right here. So the energy of the reactant in this particular case, because NO is the reactant, the reaction is NOCl goes to NO plus Cl2. Of course, that's not a balanced equation. Let me warn you, never assume that an equation I give you is balanced. You have to do that. And you guys all have the knowledge of balancing a chemical equation. So especially in a quiz, I'll just give you the reaction. In order to work it out correctly, you need to balance it. So this is the reaction. It's not balanced, but you guys can do that. And the progression is NOCl goes to NO plus Cl2. So this is the energy of the reactant. The energy of the reactant is equal to 25 kilojoules according to this particular chart. Okay, this is the energy of the product right here. This is the energy of the product. Let's say that that's 40 kilojoules, just so that you have a number to work with. So the energy of the product equals 40 kilojoules. You notice that the product is higher than the reactant. That is, the energy of the product's higher than the energy of the reactant. So you guys should know that this is an endothermic reaction. Okay, what you need is this difference right here, and that difference is 15 kilojoules, positive. So this is delta H, and it's positive. Delta H is the heats of the reaction. It's also called the enthalpy, and that's positive, and that's equal to positive 15 kilojoules. That is also the energy of the reaction. Okay, the energy of the reaction. This requires 15 kilojoules in terms of thermochemistry. Okay, that's the energy. Now this right here is the transition state, and we denote transition state by a double dagger. And the process, this species, okay, is not very stable. It doesn't last very long. Okay, but it's the morphing of the reactant to the product. And this energy, the energy of the transition state, and we use double daggered for that, is 105 kilojoules. Okay, it's a species, not very long lived, but it's still a species, and we can read it off this energy chart. Now, for this reaction to occur, we said it needed 15 kilojoules. It actually needs more than that, but that's in terms of thermodynamics. 15 kilojoules, NOCl goes to product. Okay, it requires an input of energy. It actually requires more than that, and that is called the activation energy in the forward direction. In order for this reaction to really take place, this chemical R, NOCl, needs to overcome that barrier. So what is this gap right here? What is activation energy? It's basically 105 minus 25. Because we're starting at 25 and we have to go up 105. So that's about 0, 10, 10 take away 2, that's 80 kilojoules. So that activation barrier in the forward direction, because we're moving in the forward direction, is 80 kilojoules. Okay, it's 80 kilojoules. That's the energy that we need in order to get those chemicals past that barrier. If it has greater than 80 kilojoules, then it can move on to product. In the end, you get product that has 40 kilojoules. So the net change in the energy between the products and the reactant is this delta H, 15 kilojoules positive. It's uphill. Okay. Now, if we were to move this reaction in the reverse direction, let me change my pen here. Okay, if we were to move this reaction in the reverse direction, this is my product, and it wants to go over to the reactant, because products can go back in the reverse direction as long as there are conditions by which it can do so. Okay, that is, the products are not separated by distance. They actually can collide and form the reactant. Well, what is the energy for the, what is E act reverse? Well, again, that's easy. It's the highest point it needs to achieve and its starting point. So that's going to be, I'll put it over here. Okay, let me clean my slate a little bit. I'm gonna clean it over here. So that E act reverse is going to be 105 minus, in this particular case, what do you say, 40? Okay, so that's 65 kilojoules. These things are always positive, always positive. Delta H, energy of the reaction, can be negative, but the activation energies are always positive. They always have to go uphill. Okay, they never go downhill. If they go downhill, then you have a well and it's going to stick there. Okay, so activation energy, whether it's in the forward or the reverse directions, are positive. In this particular case, for an endothermic reaction, the activation energy in the reverse direction is smaller than the activation energy in the forward direction, because it's got a smaller hill to climb. It's got a smaller hill to climb right there. Okay, so that's 65 kilojoules. So see how easy these things are to calculate. All you got to do is understand what the meanings of these terminologies are and be able to read a graph. Okay, so let's continue on with this. Let me clean this slate. Activation complex. This is the activated complex, also called the transition state. Okay, this is called the transition state. I know, that's why chemistry is so confusing. We give you so much terminologies for the same thing. Transition state is the activated complex. Okay, that's E act, the minimum energy that needs for the reactant to convert to products. Okay, in the end, the NO and Cl2 products form is more energetic than NOCl, because in our example, it was 40 compared to 25. And so this is an endothermic reaction. Here's a more detailed reaction coordinate diagram. This is a reaction you probably see in organic chemistry. This is the conversion of methyl bromide to methanol. Okay, this is a reaction mechanism. And this is, I think, called an SN1, nuclear substitution 1 reaction. Okay, you'll see that in your organic chemistry course. Anyway, what's going on here? Well, you have a hydroxide and it's colliding with a methyl bromide. This chemical right here is called a methyl bromide. And the orientation has to be correct, because what will happen is that the carbon is going to be attacked by the hydroxide in the back. Okay, and then when that occurs, this bond starts to form, but this bond starts to break. And this right here is the transition state. That's the activated complex. It can go either way. When that forms, the reaction can go in a forward direction or it can return back to the reverse direction. Okay, that's transition state, depending on the energetics of the chemical. Okay. Now, if it goes in the forward direction, then this starts to become stronger and this becomes weaker until you get the product formation, which is methanol. And so we can look at this diagram right here and say, oh yeah, this is the energy of the reactant. This right here is the energy of the product. This right here happens to be our activation energy in the forward direction. This right here is the activation energy in the reverse direction. That's why we do E act R for reverse. This right here, the energy of the product minus the energy of the reactant is delta H reaction, the energy of the reaction. And you notice because the product is lower in energy than the reactant, it's an exothermic reaction, So again, this sort of gives you more information in terms of what we are discussing. So let's take a look at this right here. Exothermic versus endothermic. You guys should recognize that this is our reactant. This is our product. It's an exothermic reaction. You can see that just by one glance. How do you know? The product is lower in energy than the reactant. Okay, it's an exothermic reaction. Now, this picture is a little bit more complicated than the illustration that we've had previously. What happens is that the reactant converts over to the intermediate one. Intermediate sits in a well, so it can exist for a longer period of time. This is an intermediate because it sits in a well. What is a well? It's a dip in that curve. Okay, so it's an intermediate. The way I would write this reaction, I would say the reactant converts over to an intermediate, and then the intermediate converts over to product. Okay, so that's the way. This is a two-step mechanism. What I mean by mechanism is that there's two steps by which products occur. The first step is forming that intermediate, which is now set up to be converted over to product. Okay, this are the transition state, however. This is a transition state for the first step. This is a transition step for the second. So this is a transition state 1, transition state 2. If you have a two-step process, then you have a transition state for the first step and you have a transition state for the second step. Okay, you always know the number of steps in your mechanism. This is a mechanism because you can count the number of humps. These are the humps right here. This is one hump, that's a second hump. Depending on how many humps you have, you know how many steps in your mechanism. If you just have this, you have a progression diagram that looks like this, then it's only a one-step mechanism. But if you have something that looks like this, then that's 1, 2, 3, 4-step mechanism, which is much more complicated. Okay, the number of humps will tell you how many individual steps you have as it progresses towards the product. It'll also give you an idea of how many intermediates, how many valleys you have. Okay, so this particular reaction coordinate diagram, it's a two-step mechanism. There's two activated complex. There's two transition state. There's only one activation energy in the forward direction. There's only one activation energy in the reverse, but there is an activation energy for the first step and there is an activation energy for the second step. This right here, let me clean this up. Okay. Oops, sorry. This right here is the activation energy for the first step. Why? Because this right here is your first step as the reactant goes from reactant to intermediate one. So that right there is activation energy for the first step. This right here, change my pen here, is the second step. And this value right here, E act 2 is the activation energy for the second step. Now, let me just make sure you are clear, because this is a note of confusion for all students who study kinetics the first time. E-act forward, that is the overall activation energy, is not equal. Again, it's not equal to E-act 1 plus E-act 2. Activation energy are not additive, okay? E-act forward is the energy, the minimum energy for the reactant, the minimum energy the reactant need to climb the highest hill. The highest hill is right here. The highest energy is right there. So what is that energy? The E-act forward is actually equal to E-act 1, because that's the energy required to get over that hill. Okay. E-act forward in this particular case is equal to E-act 1. It's not equal to E-act 1 plus E-act 2. E-act 2 is independent of the activation energy in the forward direction. Okay, it's its own independent reaction. So please keep that in mind. E-act reverse is that the energy required for the product to overcome that highest barrier. Okay, so whatever this transition state energy is and whatever that product is, that difference is your E-act reverse. It's not this first one, even though this hill is higher than this particular hill. Okay, it's where you start to its highest point. That's your activation barrier in the forward and the reverse. Whatever this difference is for the forward, this difference is for the reverse. Okay. This right here is an intermediate. So you can calculate the energy of the intermediate by just reading that energy right there. It's a species that can be isolated. So it's a species, which means that it's a defined, it's not a calculated energy. So I hope I make that clear. Okay, I hope I make that clear. You guys will have plenty of practices through this activity that we have. I'm going to clear this.
Professor?
I want to show you the second part. This right here is an exothermic, this was an exothermic reaction, exothermic. Why? Because it's downhill. This is an endothermic, because it's uphill in terms of the reactant to the product. Okay, when we're talking about thermicity, we're looking at the endpoint and the starting point. In this particular case, this particular reaction is endothermic. This right here is the delta H1. That's the energy of the reaction for the first step. It's also endothermic. This right here is delta H2. Why? Because there's two steps in the mechanism. So there's a energy of the reaction for the first step, there's an energy reaction for the second step, and there's the energy reaction overall. Same thing over here. You have delta H1, delta H2. Notice that delta H2 in this example is exothermic. That is, you're starting here, but you're ending up here. So you're ending up lower than where you start. Energy is released in that second step. First step, energy is absorbed. It's an endothermic reaction. Second step, it's an exothermic reaction. Overall, it's endothermic. Overall, it's endothermic. That is, it's uphill between here and here. Okay. So when you are studying these things, there is an overall reaction. And then there are instances where you have to study the individual step. In the individual step, there's a product in that individual step, which we call an intermediate, depending on what step you're talking about. There's also a transition state. There's also a delta H of reaction for that individual step. Okay. So this is an example of an endothermic reaction First step is endothermic, second step is exothermic. This right here is exothermic reaction. First step is endothermic, second step is exothermic. Why? Because the second step, you're starting here, you're ending up here, it's lower in energy. Your first step, you're starting here, you're ending up there in the intermediate, it's uphill, it's endothermic. I know it can be confusing because you're seeing this, well, you saw this in thermochemistry in Chem 200. It's just being given to you in the context of kinetics now, okay? But that's why I'm giving you a lot of examples, so it'll be ingrained in your head what these terminologies are, because it really is important, especially for your next modular quiz, as well as the activity that I'm giving out. So here is a summary of speed of the reaction and activation barrier. Here we have, it doesn't really matter what the reaction is, but we have a reactant in this particular case, and product. Reactant, oops, what happened? Okay, we have a reactant and a product. Right away, you know that's endothermic. How do you know it's endothermic? Because the reactant is lower in energy than the product. It's going uphill. Endothermic in terms of the overall reaction. Okay, in this case, it's a one-step mechanism where reactant converts over to product. And this is the activation energy right there, E-act. Now, let's say that the energy scales are the same. That is the scales for this reaction, and this reaction are the same. So the size of the activation energy for all three reactions are basically the same. If you take a look at this reaction, different reaction, of course, it has a lower activation energy. In this particular reaction, it's an exothermic reaction. The activation energy is lower, so it's a faster reaction. It's a faster reaction. Why? Because there less energy is needed to overcome that barrier. Here, more energy is needed to overcome that barrier. So this is a slow, this is a fast, but this is even faster than the previous. Why? Because look at that barrier, that activation barrier. It's even lower than the others. This would be an endo, this would be an exo, and this would be exo. Okay, if we had numbers in the energy scale here, we could read off the transition state, the energy of the reactant, and the energy of the product for all of these, if we had a scale. So these illustrations kind of shows you the correlation between activation barrier and the speed of the reaction. Okay, clear this. Oops. Reaction A, endothermic, activation energy is high. Reaction B, exothermic, activation energy is lowered, so it's faster than the previous one. And finally, reaction C, exothermic as well, is the fastest among the three. Fastest among the three. So let's look at the Maxwell-Boltzmann distribution plot. We haven't discussed the Maxwell-Boltzmann distribution plot yet, but if you recall, the Maxwell-Boltzmann distribution plot gives you the energy of a collection of chemicals. So suppose we have a container and there's a bunch of chemicals in here. And we say that we expose this container to a temperature, say 25 degrees. Well, 25 degrees, you can actually calculate the average energy at 25 degrees. But the Maxwell-Boltzmann distribution plot tells you that the energies of the chemicals in this container at 25 degrees are going to vary. Some are going to have low energy, some are going to have a high energy, but there's going to be an average. And you can calculate something that called the root mean squared velocity by which they move. Okay, hopefully I'm jarring your head in terms of gas laws. Don't worry about URMS though. Okay, what you want to look at is this right here. At low energy, you have a profile diagram that looks like this. It has an average energy. This would be the average energy. And as we raise the temperature, say from T equals 25, T equals, say, 35 degrees. Remember, we changed the temperature to 10 degrees above its original, the reaction rate doubles. Again, rule of thumb, just as a reminder. But look what happens to the Maxwell-Boltzmann distribution plot. It shifts. It shifts to the right. Okay? But notice the distribution of energy. Again, let me explain the Maxwell-Boltzmann distribution plot because it's really important to understand this. At 25 degrees, some molecules have near zero energy. That is, they're just staying put. Some molecules have very, very high energy. They're moving very fast. And there's a distribution between these two range. So the X represents population of chemicals. And some of them will be slow. Some of them will be fast. And this is the population. Okay. And most will have an average. The average, like, well, taking the average of the slow and the fast one, and it's right in here. Okay. But notice that some of them will have some sort of energy that surpasses this line which I will call E act. Okay, I'll call that E act. And this population in purple are the chemicals that surpasses that E act. What happens when I raise the temperature? When I raise the temperature, that curve shifts to the right. That is, more of the population are going to have higher energy. Why? Because we increase the temperature. We put in some energy in there. Okay, so they're moving faster. Some of them will still have zero energy. Some of them will have, in fact, some of them will even have higher energy than the previous temperature. And it's going to have, the average is going to shift to the right. But look at the population now that overcomes that E act. The population now has increased by that amount. So that means you have more chemicals at the higher temperature that can overcome that activation barrier. This amount more. Why do you think when we raise the temperature, we also increase the rate? It's not because we lower the activation barrier. The only thing that will lower the activation barrier is through a catalyst. That barrier is always fixed depending on the chemical reaction you have. What happens when we raise the temperature is we provide more energy for more of the chemical population to overcome it by that much. And by giving them more energy, they can now easily go over that barrier and reach the other side. That's why the energy, the reaction rate increases at higher temperature, because now more of the chemicals will surpass that activation energy that was not readily available at the lower temperature. Okay, so think about that a little bit more, because that really is an important topic. That is really an important topic in terms of why temperature increases the reaction rate, because you give it more energy in terms of the population. Okay, so here are the wordings for that. Oops, sorry. Okay, that's what the Maxwell-Boltzmann distribution allows you to figure out. Okay, now this is an energy in this Maxwell-Boltzmann distribution, but this tells you how that energy translates to population. How much of the population increases because it now overcomes that activation barrier. That right there is the activation energy is proportional to the activation energy R times T. T is the absolute temperature. That means you have to quote the temperature in kelvins. R is 8.314 joules per mole Kelvin. Okay. don't use 0.08206. 0.08206 is gas loss. 8.314 comes to thermochemistry, thermodynamics. Because we convert liters, atmosphere. In fact, you can do this if you want in your spare time. If you convert liters, atmosphere in 0.08206 to joules, that 0.08206 will convert over to 8.314. Okay, so we use this right here for our R. I'm going to skip over this part. It's a very important concept, but I want you guys to learn it on your own. Read it, look for it in your textbook, read the context here. There's actually an extra credit question in the assignment. And so this is the explanation for that. I want you to learn it on your own, okay? And then answer this question in that assignment in Canvas. How does the Maxwell-Boltzmann distribution plot explain why the reaction favors the reactant for an exothermic reaction and why it favors the product for an endothermic reaction? I know that this looks like a confusing question. Go to Canvas, go to the assignment. I opened it up today. If you can answer it tonight, then I'll give you points for that. It's due tomorrow, 24 hours, okay? But remember that when you raise the temperature, you increase the rate of the reaction. But for an endothermic reaction, you actually favor the production. You actually favor more products being formed, but for an exothermic reaction, you actually favor more reactant to form. Okay, it seems to be contradictory in terms of an exothermic reaction, but that's why I posed that question. I want you guys to learn it on your own and answer that question. Okay, so let me kind of summarize what we've just talked about in terms of the Maxwell-Boltzmann distribution plot and the activation energy. So we have a rate. Remember the rate law? Rate law is equal to K times some concentration of A, depending on what reactants are involved, taken to the X power. B, if we have more than one reactant contributing to the reaction, taken to the Y power, etc. Okay. The Arrhenius equation actually gives us K. The Arrhenius equation gives us information about the rate constant K. Okay, so the rate is going to be equal to the collision frequency and the orientation, and that's the pre-exponential factor. And then the activation energy, which is this right here, okay, times probably what we have is the concentration of A taken to the X power, concentration of B taken to the Y power, etc. This right here is your K value, right there. If we expand that, rate is equal to A, that's your pre-exponential factor, that is your activation energy, and this right here are your concentrations. Basically that. Okay, K is the pre-exponential factor A and the activation energy. And then these are the concentrations. That's your Arrhenius equation. I want to explore this equation more because it really is important in the context that we are talking about. So let's take a look at K. K is your rate constant, and it's equal to this right here. That's K. Now, if we make K equal to that, that's basically this term, pre-exponential term, and the activation energy term. K is equal to E to the minus EA over RT, where EA is the activation energy. E to the minus EA over RT tells you how the population is weighted. Okay, tells you the weighted of the population that will contribute to the rate constant K. A, don't worry about A because we get that through statistics. We generally give it to you, or you can calculate it through other means. We're not going to ask you to calculate it through statistics. But I want you to look at this equation because we're going to expand it and take the natural log of both sides. And when we take the natural log of both sides, then we have natural log K equals natural log A, and then this whole term drops down from the exponent. Okay, it's not e to the minus EA, it's just EA over RT. So this equation tells you that the rate constant K is equal to the pre-exponential factor A. In fact, those two have to have the same units. A and K have to have the same units. Why? Because this factor right here is unitless. It's unitless. Okay, it just gives you a weight by which to figure out how much of the population is going to contribute to the rate constant. But it tells you that the rate constant, the natural log of the rate constant, is equal to the natural log of the pre-exponential factor minus EA over RT. EA over RT throttles the amount of chemicals that are going to contribute to the rate constant. But more importantly, if we make this into a mx plus b, then what we have is an equation of the line. We always want the equation of the line. Okay, in science, we always want to do that. So when we do this, then natural log A, that is the pre-exponential factor, is equal to the intercept. 1 over t is our independent variable, okay, x, and EA over R is the slope. So we can actually calculate the activation energy if we have a series of experiments and we calculate the slope. So this is an equation that you guys will actually be doing in experiment number 1, or experiment number 1, the kinetics lab. Okay, so notice that this term right here becomes y equals mx plus b. There is a question here, is EAC reverse EAC to? Yes, generally, depending on what you're referring to, okay, in a diagram, if you're only looking at one reaction step, then EAC 2 generally, no, EAC 2 it refers to the second step. Reverse is actually going from the product all the way to the reactant. Okay, so you have to look at the specific reaction that you have in order to reference whether it's EAC 2 or E reverse or EAC reverse. Okay, it's based on the context of your perspective, in other words. I want to finish this off because we're running, it's almost coming up to 6:15. Okay, so here's a diagram. If we plot the rate constant at different temperatures, okay, that's why your first experiment monitors the methyl viologen at different temperatures. If we plot natural log K, the rate constant, versus 1 over temperature. So this right here is 1 over temperature. This is natural log A, oops, right here. Then the slope of that line is EA over R. And if we multiply the slope times R, then we have the activation energy. And it's always going to be positive. The slope is negative, but remember that the slope according to this reaction right here is negative EA over R. So the activation energy is positive. If you take the slope and multiply by R, you got the activation energy. Okay, so that's how we do the Arrhenius equation. If you have 2 points in your graph, and this is especially true for the group work activity that I presented, you have 2 points, 2 temperatures, then you can actually use this equation to figure out what the activation energy happens to be. All you really need is 2 points in order to get a straight line. Remember that in math? If you got 2 points, you can get a straight line. If you got a straight line, you can calculate a slope. And the slope in this equation will give you the activation energy. Okay, so I'm going to skip catalyst for now. I'll come back to it, but I think I talked to you guys last time. We talked about this equation, and this equation is the Arrhenius equation. Really gives you information about the rate constant. Okay, the rate constant. And what exactly is the rate constant? It's the constant that doesn't change if you change the concentrations. It does change if you change the temperature. Okay, it's the reason why it's called a constant, because it doesn't change. But you guys will learn as well in equilibrium that a constant is a constant unless the temperature is changed. Once the temperature changes, then that number varies. So if you, a reminder, if we have the rate law, and the rate law will look like this: rate equals K, that's the rate constant, times some concentration of the chemicals that are going to be proportional, that determines the speed of the reaction. Let's say A to the X. Remember, X is the order. Say B to the Y, depending on which chemicals are going to be participating in the rate of the reaction. You might even throw in a catalyst in there. And these chemicals, A, B, catalyst, are generally what are in your reactant, are the chemicals that you use to start the reaction. Now, not all of them may be used, maybe only some of them. Catalysts may or may not be part of the rate law, but it's a good bet that you guys can put it in there and then see whether or not the order of the catalyst is 1 or higher. Remember, if it's zero order, that means that it's not it doesn't influence the speed of the reaction, because anything to the 0 power is just 1. So it's independent of that chemical. So this right here represents K. Okay. And that's what you see here. Let me clean this. Okay, that's what you see right here. This is K. And then the concentration taken to whatever power that you have. And that's basically what I have right there. And so what you can do is this. We always try and do this in science. And when you guys do experiment number 1, it's no different. You guys are going to take the different temperatures, figure out the rate constant at those different temperatures, and then calculate the rate, basically the activation energy. Okay, so we talked about this last time, where we took this equation right here and set it equal to K, because that is K. And then we, in order to get rid of the exponent right here, we take the natural log of both sides. And when we take the natural log of both sides, what you get is this term right here drops down to the equality, and then it's the natural log of K equals the natural log of A minus the activation energy over RT. Notice the negative sign. The negative sign tells you that when the activation energy is higher or large, okay, that's what the negative sign says, is that the activation energy is large, the rate constant gets smaller. It makes sense. Again, the math tells you the story. A high activation barrier means that the chemical will need more energy to get past that. High activation barrier makes the kinetics slower. Okay, so the negative sign there has meaning. Look at the 1 over T. It's the reciprocal. Okay, it's the reciprocal. So that means that if you have high temperatures, you're going to get, again, because it's a negative, at high temperatures, you're going to get the population higher in terms of what chemicals can go over the activation barrier, and therefore your rate's going to increase, okay? Lower temperature, you have less of the population making it over the activation barrier, and so your rate's going to decrease, okay? In fact, you can see from this equation that T is going to change the value of K. T is going to change the value of K. Okay, so different temperature changes the rate constant. The activation energy, however, is always fixed. That's a fixed number. You cannot vary the activation energy, even if you change the temperature. The only way you change the activation energy is if you take that reaction and run it, and you run it through a different mechanism, say a catalyst is used. Okay. The other thing I want to point out is that natural log K, natural log A, they are going to have the same units, okay? The units of K and the units of A are the same. Minus EA over RT is unitless. Okay. It's unitless. It just weighs the population of the chemicals that are going to contribute to making it past the activation barrier. So again, it's what makes Chem 201 so fascinating, is that the chemical process, the events that takes place is nicely explained by the mathematics that is used to derive what goes on. And you see that throughout this course. We have a mathematical equation, and if you know how to interpret it correctly, you're going to know the meaning of what's going on at the chemical level. Okay, and that's the same thing here. So what we do, of course, is we take this equation and we write it in the equation of a line, y equals mx plus b, and now you can basically make a plot of the reciprocal of the absolute temperature. Remember, it has to be in Kelvin. And the natural log of K, remember that each temperature is going to give you a rate constant unique to that temperature. Okay, so this might be temperature 1, this might be rate constant K1. This might be temperature 2. This right here will be rate constant K2. That rate constant is going to be correlated to that temperature. Okay, you change the temperature, you change the rate constant. But if you take the natural log of the rate constant and you plot it against 1 over the absolute temperature, you get this line. It's going to have a negative slope, and that slope, M, is equal to negative EA over R. So in order to calculate the activation energy, E act, you take the slope from that experiment or that data set, and you multiply it by R. And remember that R is 8.314 joules per mole Kelvin. And then the intercept here, that's the intercept where the line goes through the y-axis at x equals 0 or 1 over t equals 0. Okay, well, that's the natural log of A. That is the natural log of the pre-exponential factor. If you want to figure out what the exponential factor is, then take e to the natural log A, and that'll give you pre-exponential factor. So remember, the inverse of a natural log is taking the exponent. Here is a nice little equation if you just have 2 points. Certainly you can derive what the slope and the intercept is if you just have 2 points, because 2 points will give you a straight line. Okay, 2 points will give you a straight line. So you can basically figure out what the slope and the intercept is, which is the information that you need in kinetics. Or you can just use this equation. You can just use this equation. It'll get you the same place. Okay. So hopefully you guys will see, you guys will have a lot of practice actually of using this equation, not only in the activity that you have in lab, but also the experiment that you guys will be carrying on next week actually. So let's take a look at the other factor in here. Of course, these are chemicals, A to the X, but we might also have a catalyst in here that is part of the rate law. And what exactly does a catalyst do? It basically changes the pathway by which the reactant, the starting material, gets to product. The net stoichiometry is still the same. That is the material that you have in the beginning to produce the product are going to be the same. It's just that the catalyst will give it a different mechanism, a different pathway to get there. And because if you have a different pathway, then that activation energy might be lower. In fact, if it's not lowered, it's not a catalyst. If you put in a chemical that makes the activation energy higher, then it basically inhibits the reaction. It would not be a catalyst. A catalyst, by definition, is a chemical that accelerates the speed of the reaction, but itself is not used up. What will happen is that the chemical will get used up in one of the steps in the mechanism. So it's going to be part of the chemical change that the reactant undergoes. But at the end, some place at the end, it may not be the last step, the catalyst is regenerated. Okay, it's regenerated. And so it'll be cross out in the net reaction. You start with chemical C in the beginning, which is a catalyst, and then you generate chemical C at the end, which is the catalyst. And when you do the net reaction, you'll see that it cancels out. So that's basically what's going on here. It decreases the activation energy. It doesn't, because it decreases the activation energy, now more chemicals will have sufficient energy to make it over that activation barrier. Like this is my reactant, and originally the uncatalyzed reaction would have to go through this activation barrier, E-act, right there, forward. But when put in a catalyst, it takes it through a different mechanism. So the activation barrier is going to be, again, from where it starts to the highest peak, that would be the E-act, forward, catalyze. Okay, that would be the activation barrier, the activation energy, and that number is much lower than the original. It means that more chemical can overcome that barrier, more chemical will go over to the product. But notice, because the catalyst drops the activation energy, okay, it drops the activation energy, then the forward reaction is fast, but the reverse reaction can also be fast because it also lowers the activation barrier for the reverse direction. Okay, it lowers the activation barrier for the reverse direction. Just because you add a catalyst, that product is not going to take the original path. It's going to take the same pathway in which the reactant gets there. So it basically causes the reactant to go to product faster. It also causes the product to return back to reactant faster. But the net change, basically, because in this particular case, what we're trying to do is get more products, is a faster production of the product. Okay, faster production of the product. So again, these are just examples of trying to go from point A to point B. And what you might have to do, again, trying to simplify things, is you might have to go over some rocky terrains. But if you can find a shortcut, you still get to the same destination, except it's going to be an easier pathway. Okay, and that's what a catalyst does. And we see examples of catalysts everywhere. Your catalytic converter. These days, just a few weeks ago, I think there was a big increase in people actually going to cars and sewing off the catalytic converter, okay, of cars. And so people would start their car, and then they would hear this large not even muffle, large engine sound coming from the bottom of their car. They look down and someone's chopped the catalytic converter. Why? Because the catalytic converter has precious metals. In fact, with the stock market up there, the precious metals have, like gold, it's going through the roof in terms of the prices. So what they do is they take the catalytic converter, isolate the precious metals, and then sell them in the black market or whatever. But the way a catalytic converter works is the following. You have gasoline. This is your hydrocarbon. And when gasoline goes into your engine, it feeds into your engine. Maybe you might have fuel injector. The cars these days, they have a different mechanism by which it feeds some of you might know, the gas, the fuel into the engine, okay? But it also needs air, oxygen, because you need a combustion reaction. So a combustion reaction is where you take a hydrocarbon, oxygen, you form CO2, and energy. But sometimes the combustion is not complete, and so you might form some carbon monoxide. Okay, you might form some carbon monoxide. That's because there is insufficient oxygen for that. It might get throttled. But the other thing that engines will do is when it sucks in air, it doesn't isolate just the oxygen. It also takes in nitrogen. Remember, nitrogen's about what, 81% of air. So there's a lot of nitrogen in there. And when nitrogen is burned in the presence of oxygen, you get NO. NO is actually nitrous oxide, and that's the reason why you might have smog above a city, especially when there's high traffic. It's that chemical right there that will react with oxygen further to form NO2, to form smog. So back in the 1970s, they actually tried to eliminate this poisonous chemical smog and also decrease the amount of CO by introducing a catalyst that will take these chemicals, CO and NO2, and produce CO2 and nitrogen gas. Now, nitrogen gas is perfectly fine. It's a safe gas. It doesn't contribute to greenhouse. Carbon dioxide, however, does contribute to greenhouse, but it's much more safe than CO. CO will kill you. As you guys probably have read in Texas, where people were turning on their car, turning on the heater and trying to get warm. But if they're in the garage, then the CO accumulates. And because it's a silent killer, they don't even know that CO is there, and they basically get starved of oxygen, because CO binds to your hemoglobin a lot more efficiently than oxygen. So it basically displaces the oxygen in the hemoglobin. And because there's no oxygen there, then your tissues don't get the oxygen required to burn the fuel, okay? What the catalytic converter does, however, is it takes in these gas, NO2 and O2, and this is the mechanism right there. It basically sits on these precious metals. These are the precious metals right here, okay? And then it causes the NO2 to break apart. One of the oxygen comes apart, and then it sort of migrates to CO. And when it does that, then you get CO2. There's another chemical there. Two of the oxygens kind of break apart, and then you get nitrogen and another nitrogen forming to form nitrogen gas. So again, very clever chemists back in the 1970s figured it out. The catalytic converter drops the activation barrier for that particular reaction to a very low level. And so that particular reaction can take place as the gas is basically whisked through the catalytic converter. What people will do will take the catalytic converter, open it apart, and then find these precious metals. The other catalyst out there that is common is what is in you and me, enzymes. Enzymes are great catalysts. All the chemistry that occurs in our body is catalyzed by enzymes. As a smog inspector, I can attest that the cat being still okay. So someone here is a smog inspector. Okay, online you can find metal plates and you can install to cover your cats. So I guess there's, yeah, a lot of them are being, catalytic converters are being taken away. So you got to be careful. Hopefully you have a car alarm so it sets off when someone goes under. But again, if it's stolen, that can cost you 1,000 or more, okay, in terms of replacement because of the precious metals. So hopefully it doesn't happen to you, but there's a high incident out there. As I was saying, enzymes in your body, it speeds up the chemistry that occurs in your body. And without enzymes, we probably would not function. The food that we eat would just stay in our stomach and it would not be digested. The alcohol that we drink will never get metabolized. So we'll see more about enzymes in the next section. So here's just a review of what we talked about. These, you guys should recognize among these four scenarios, which are exothermic. Remember, exothermics when the energy of the product is lower than the energy of the reactant, which is endothermic. The energy of the product is higher than the energy of the reactant. Which one is fast relative to the others? Which one is slow? Okay, slow means high activation energy. Fast means low activation energy. These are the activation energy in the forward direction. It's always from where you start to its highest peak. Always from where it starts to its highest peak. Even if you have a scenario like this, suppose you have a scenario like this where you start here and this right here is your, this is a two-step process. And you might say, yeah, but this hill is higher than this hill. There's two activation energy here, okay? It doesn't matter the climb, it matters the distance. Go back, it matters the distance. So this energy gap right here is the highest from where you start to the highest peak. That's your activation energy overall for the reaction. Yeah, this is the activation energy for the first step. This is the activation energy for the second step. But this is the activation energy overall. And likewise in the reverse. Likewise in the reverse. And you do not add activation energies. Activation energy overall does not equal to activation energy 1 plus activation energy 2. Okay, you guys should know at this point what this diagram has. It's a two-step mechanism. This would be EAC 1 because that's the first step. This would be EAC 2. And notice EAC 2 is not EAC reverse. It's not. EAC reverse is this right here. It has to go all the way past that hill to get to the other side. EAC 2 is not EAC reverse. Okay, this would be EAC forward. What you do is you identify the highest species and you calculate your overall activation barrier, forward and reverse, based on that highest energetic chemical. For the forward, it's this minus this where you start. For the reverse, it's this minus that where you start. And then each individual step has an activation energy. Each individual step has an energy of the reaction. Okay, so when you work in that group, I'll break you up into your group, okay, right now, at least in the next 5 minutes, get the names of your group and communicate, because you guys will have like a week and a half to work on this.